Something is wrong with the visitor from another star, and it's defying the laws of physics right in front of us. This isn't a gradual change, not a slow cosmic fade. This is an abrupt, jarring transformation happening at a speed that has dismantled the calm predictions in every astronomer's model. Between November 28th and December 3rd, in the cold, silent expanse between Mars and Earth, the interstellar comet known as 3I Atlas underwent a metamorphosis that should be impossible at this distance from the Sun. Its vibrant emerald green coma, the classic signature of a healthy, outgassing comet, vanished completely. In its place, observers from mountaintops in Chile to backyards in Tasmania began reporting a colour that sent a chill through the astronomy community. A brilliant, unwavering, reflective gold. Not the dull yellow of dust, not the white with a tinge we sometimes see, but a deep, burnished, almost metallic gold, like a coin held up to the sun. This shift is more than an aesthetic curiosity. It's a crisis in comet science. Gold, in the strict vocabulary of astrophysics, means the gas is gone. It means dust dominates. It means the volatile ices, the water, carbon dioxide, carbon monoxide that boil off in sunlight to create the beautiful streaming tails and fuzzy comas have fled or frozen silent. Subscribe to this channel and hit that like button is how I know you're out there, part of this global vigil, and comment below, where are you tuning in from? What time is it where you are right now? Let's map this watch party across the planet, and if you believe in patterns, if you trust the grim precedent written across our own sky just days before, gold means fragmentation is next, because we have seen this exact movie play out already, frame by terrifying frame. Comet C 2025 K1 Atlas, a native of our own solar system, turned the same impossible gold on November 22nd. On November 29th, it shattered into at least 3 distinct pieces, a cloud of rubble fading into oblivion. Now the interstellar visitor, 3I Atlas, is following the same brutal script, green to gold in days, in the same region of the sky, with the same eerie timing. Coincidence? The human mind desperately wants to believe it is. But the data, cold and relentless, suggest otherwise. It suggests that location in space, this particular patch of sky we call the constellation Leo, might matter in ways our textbooks never dared to admit. We are now on a collision course with a fundamental revelation. Stay with us through December 19th. Because in the profound darkness of a new moon, with the world's greatest telescopes trained on a single point of light, we're about to watch an ambassador from another star system either survive its passage or shatter into cosmic dust, and the answer, either way, will rewrite a chapter in our understanding of the universe. If this story has your heart pounding like it has mine, if you feel that primal pull to witness a mystery unfold in real time, then you need to be here for what comes next. Let's rewind to understand the depth of the anomaly. 3 weeks ago, 3I Atlas was exactly what we expected an interstellar comet to be. Strange in origin, but familiar in behaviour. It came screaming into our solar system on a hyperbolic orbit, a trajectory that proved it was a born in the disk of another star, ejected by gravitational chaos and destined to leave ours forever. As it crossed the orbit of Mars, solar heating began its work. Ice sublimated, gas erupted from its frozen nucleus, and like countless comets before it, it glowed with that specific ethereal green. That colour is a hallmark of chemistry we know intimately. It comes from diatomic carbon molecules, C2, breaking apart under the sun's ultraviolet fury, releasing photons at a precise wavelength our eyes see as emerald. It was a beacon of normalcy. Yes, its home was unknown, but its language was one we'd spoken for centuries. It was following the rules. Then, in a window of time shorter than a single Earth week, the rules were ripped up. The green didn't fade gradually. It was there, and then it wasn't. Reports flooded in from coordinated observation networks. The object in their eyepieces and on their CCD screens was no longer green. It was gold. The initial reaction was universal skepticism. It had to be an artifact, a trick of the atmosphere, a glitch in the colour calibration of a camera sensor, a misinterpretation of data. This is the first defense mechanism of science. Assume the error is yours. But one by one, the excuses were systematically annihilated. The European Southern Observatory's very large telescope in the Atacama Desert, peering through some of the driest, clearest air on Earth, confirmed it. The Keck Observatory atop Mauna Kea in Hawaii, above 40% of Earth's atmosphere, saw the same golden hue. The Southern African Large Telescope, the instruments in the Canary Islands, independent teams using different hardware, different software, under different skies, all returned the same impossible result. This was real. The comet had changed its fundamental nature in less than 168 hours. To understand why this is catastrophic for our models, you have to understand comet color as a diagnostic tool. It is not arbitrary. It is a direct readout of physical processes. A green or blue comet is a gas-dominated comet. Sunlight is being absorbed by simple molecules and re-emitted at specific colors. It's an active light source. A red, orange, or yellow comet is a dust-dominated comet. Sunlight is simply reflecting off countless tiny grains, and warmer tones mean the grains are larger, filtering out the blue light. But gold is in a rare category of its own. Gold suggests a very specific, refined kind of dust, not the fluffy, microscopic snowsoot of a typical comet. It suggests larger grains, perhaps tens of microns in size. Fine sand, essentially, with highly reflective, possibly metallic or polished silicate surfaces. It suggests the chaotic scattering of small particles has ceased, and now only these larger, heavier, more orderly grains remain, reflecting sunlight in a coherent, warm metallic sheen. It is the colour of a comet that has stopped breathing. Now consider the location. 3i Atlas made this shift at roughly 1 astronomical unit from the Sun, the same distance Earth orbits. At this range, solar energy is more than sufficient to violently sublimate water ice, to blast apart carbon molecules. This is the heart of the activity zone. A comet here should be at its most vibrant, its most gassy, its most green. The coma should be swelling, the tail lengthening. Instead, it went silent. In less than a week, it transformed from a chemically active, volatile-rich body into what appears to be a passive, dust-covered reflector. No standard model of comet evolution has a line on its graph that plummets from active to inert so quickly at this heliocentric distance. The phase angle, the geometry between the Sun, comet and Earth, was checked and rechecked, as this can affect apparent colour. It couldn't explain this. Atmospheric distortion was ruled out by space-based assets and high-altitude observatories. Raw spectroscopic data, the unassailable fingerprint of light, confirmed it. The emission lines of carbon were gone, replaced by a smooth reflective continuum shifted toward longer, redder wavelengths. This was a real, physical, and terrifyingly rapid change happening to an object from another star. We are watching something we have no right to see at this stage. Comets do evolve, of course. They often start reddish in the outer darkness, reflecting a dusty, primitive crust. As they warm, they wake up turning blue and green without gassing. If they survive their close brush with the Sun, dust production can later surge, pulling their colour back toward orange. But this symphony plays out over months or years, a stately, predictable movement governed by distance and composition. 3i Atlas has taken the crescendo of that symphony, the transition from gas to dust, and compressed it into a single, dissonant chord lasting 5 days. That isn't evolution. That is an event, something abrupt, something catastrophic, or something we have never ever documented before. So what phase, what terrible and final phase did 3i Atlas just enter? The answer is keeping astronomers across the globe awake, staring at data and drinking cold coffee. Because there is one scenario in the literature, one documented precedent, where a comet turns gold this quickly. It happens when the comet is about to die, and we don't have to look back through dusty archives to find it. We have a fresh corpse, still cooling, that followed the same script step by step until it came apart. That corpse has a name, K1 Atlas, and its story is a warning written in fire across our own celestial backyard. The precedent, the ghost in the machine that haunts every observation of 3i Atlas, is a comet that was never supposed to be remarkable. C20 K1 Atlas was a native, a citizen of our own solar system, born in the icy vastness of the Oort cloud. It was discovered in May of 2025, a routine addition to the catalogues, and for 6 months it behaved with perfect, predictable decorum. It followed a long-period orbit, inbound toward the Sun, brightening steadily, developing a textbook green coma and a faint structured tail. Observers tracked it as part of their regular surveys, noting its progress, but it didn't command special attention. It was just another comet. one of dozens discovered every year, making its first and perhaps only pilgrimage to the inner solar system. It was, in every sense, normal. Then, in mid-November, the normalcy began to fray at the edges. Sharp-eyed observers, the ones who monitor spectral lines as closely as brightness, noticed something subtle. The green emission lines, the specific fingerprints of diatomic carbon and cyanogen, were weakening, not because the comet was getting fainter overall, but because the gas producing that signature glow was diminishing relative to the dust. It was as if the comet's engine was sputtering. The change was confirmed across multiple observatories. By November 22nd, there was no longer any room for subtlety. K1 Atlas had turned gold. The transformation was as stark and complete as the one we've just witnessed with 3i. The vibrant green coma was replaced by that same brilliant, reflective, warm golden hue. The community was stunned. For a comet at its distance, still well outside Earth's orbit and moving toward greater solar heating, this was a profound and ominous sign. The chatter on astronomer forums and Slack channels shifted from casual observation to urgent concern. Gold, in their experience, was the colour of a comet's last act. They began pointing every instrument they could at K1, watching with a morbid scientific fascination. They didn't have to wait long. 7 days later, on November 29th, high-resolution images from the Gemini Observatory and the Hubble Space Telescope told the definitive story. The single bright nucleus was gone. In its place were at least 3 distinct condensations of light, each sporting its own faint dissipating halo. K1 Atlas had fragmented. It didn't explode. There was no violent detonation. Comets are too fragile for that. Instead, it came apart along its internal fault lines, like a clod of dry soil crumbling in your hand. The fragments, each perhaps dozens of meters across, began drifting apart at a leisurely speed of a few meters per second, a walking pace on a cosmic scale. They continued along the original orbital path, a grim little convoy of debris, but their fate was sealed. Without the structural integrity of a single nucleus, each piece would sublimate and disintegrate faster. Within weeks they faded from view, not with a bang, but with a whisper, becoming just another anonymous cloud of dust enriching the zodiacal light. The comet was added to the long list of solar system casualties. Now, overlay that timeline with the interstellar visitor. 3i Atlas turned gold roughly on December 3rd. That places it on the exact same sequence, green to gold in a matter of days. The question now hangs in the air, thick and unavoidable. Gold to what? If the pattern holds, if this is not some cruel trick of cosmic coincidence, then 3i is reading from a script whose final page we have already seen, and that script ends with disintegration. The statistics scream for attention. Gold coloration in comets is exceptionally rare. Most professional astronomers will never see it in their careers. Survey a century of literature, and you might find a dozen well-documented cases. It requires a very specific and terminal set of conditions. The object must lose its volatile ices catastrophically fast, or have them be so depleted that the dust mantle is left completely exposed with no gaseous haze to diffuse the reflected sunlight. This typically happens to ancient exhausted comets that have made countless passages by the sun, their ices finally spent after millennia of service. Or it happens to comets suffering a sudden structural collapse, a massive outburst that blows off the volatile shell in one go, leaving a barren, dusty core behind. For 2 comets, in the same month, in the same region of the sky, to undergo this same specific rare transformation defies any comfortable explanation. Scientists, rightly cautious, hedge their language. They speak of correlations, not causations. They point out the fundamental differences. K1 was a pristine Oort cloud object, likely on its first visit. 3i is interstellar, thermally processed, a visitor from an alien system. They are taxonomically as different as a wolf and a whale. Comparing them, they argue, is scientifically perilous. The mechanism that broke K1 tied to its pristine, fragile structure shouldn't necessarily apply to the baked, possibly denser core of 3i. But the timeline is an insistent immoral fact. The sequence, green, gold, breakup, doesn't care about taxonomy or origin, it simply is. And when you stare at the 2 light curves, the 2 sets of spectra, the 2 trajectories both slicing through the constellation Leo, the sheer weight of coincidence becomes a burden. It begins to feel less like chance and more like a clue. Researchers are now engaged in a frantic global archaeological dig through archival data. They are searching for other examples, any other comet in the historical record that turned gold and then fragmented. They are trying to build a statistical case to see if gold is a reliable diagnostic of imminent fragmentation, or if K1 and 3I are just two flukes that happen to land on the same number on the roulette wheel. The data so far is agonizingly thin. The sample size is minuscule. We are, as one astronomer put it privately, flying blind through a phenomenon we don't understand. But the urgency is palpable, because 3I Atlas is not just a scientific curiosity, it is a once-in-a-generation opportunity. It is the first interstellar comet we have ever tracked with modern instruments during such a critical, potentially terminal phase. We watched Oumuamua as it was leaving, already inert. We watched Borisov from a distance, forever active and healthy. 3I is giving us a front-row seat to its potential death throes, and in doing so it may reveal universal truths about how all comets die. This brings us to the detail that is hardest to dismiss, the one that nudges the conversation from intrinsic properties to something more unsettling: location. Both comets were in the constellation Leo when they turned gold. Both were exhibiting profound stress in the same patch of sky, and both, if the pattern holds for 3I, will reach their terminal phase while still positioned against the backdrop of the Lion stars. Constellations, of course, are human inventions, imaginary pictures drawn on the celestial sphere. The stars of Leo are not physically connected. Regulus is 79 light-years away, Denebola 36, Algebra 126. They share nothing but a line of sight from our tiny planet. For two comets to pass through Leo in the same month is statistically unremarkable. Space is vast, but our sky is full of comets tracing great arcs. They cross all 88 constellations eventually. But for two comets exhibiting an identical rare behaviour to do so in the same month, in the same 2.3% of the celestial sphere, the probabilities begin to multiply, compressing the odds of pure chance into a very narrow, very uncomfortable corner. The human brain, engineered by evolution to find patterns where they may or may not exist, rebels at this stacking of improbabilities. At what point does a series of coincidences become evidence of something else? The scientific mind is trained to resist this impulse, to demand a mechanism, a physical how. But quietly, in the back channels of science where half-formed ideas are allowed to breathe, a question is being asked with increasing seriousness. What if location matters? Not in an astrological sense, but in a real, physical, environmental sense. What if the patch of space corresponding to the stars of Leo during this specific window of time is somehow different? To understand the non-random hypothesis, we must first banish the ghost of astrology entirely. What is being proposed is not that the stars of Leo exert some mystical influence. It is that the three-dimensional volume of space that our line of sight to Leo passes through might possess unique, measurable physical properties at this particular moment in the solar cycle. The key lies not in the distant stars, but in our own sun's dynamic, messy influence. The sun does not emit a smooth, uniform solar wind. Its magnetic field, twisted and complex, structures the heliosphere into distinct sectors. The most prominent feature is the heliospheric current sheet, a vast, wavy boundary where the sun's magnetic polarity flips from north to south. Imagine a spinning ballerina's skirt that ripples and warps as she turns. As the sun rotates every 27 days, this current sheet sweeps through the solar system. Regions on one side of the sheet have a magnetic polarity opposite to those on the other, and the sheet itself is a zone of intense activity. Higher densities of charged particles, stronger magnetic field gradients, and more turbulent plasma conditions. This is established, mainstream heliophysics. Spacecraft have been measuring these sectors for decades. Your GPS and satellite TV depend on models of this space weather. Now consider a comet as it voyages through this structured environment. It is not travelling through a perfect vacuum. It is moving through a medium laced with magnetic fields, streaming particles, and shifting pressures. For most of its journey, these variations are negligible, mere background noise. But what if, during its passage through a specific sector, particularly a disturbed high-pressure sector near the current sheet during solar maximum, the environmental stress on the comet ratchets up significantly? Could enhanced solar wind pressure accelerate the stripping of a comet's tenuous atmosphere? Could intense fluxes of charged particles cause unusual surface charging, leading to electrostatic forces that pull weakly bound dust grains away? Could magnetic turbulence interact with any ionized material in the coma, transferring energy and creating localized heating? The hypothesis is that when a comet's trajectory intersects one of these bad neighborhoods in the heliosphere, its evolution can be accelerated or destabilized. The gold color in this framework is not just about running out of gas, it's about having that gas violently and rapidly stripped away by an external environmental factor, leaving the dust behind in a sudden, shocking unveiling. The fragmentation that might follow is then the inevitable result of a nucleus whose structural glue has been catastrophically removed, leaving it unable to withstand even its own gentle rotation and thermal stress. This is the quiet, radical idea circulating among some comet scientists. They are not yet writing papers on it. The evidence is too circumstantial, but the correlation is too compelling to ignore. Both K1 and 3I passed through Leo within weeks of each other. We are currently at the peak of solar cycle 25, a period of heightened solar activity. Sunspot numbers are high, coronal mass ejections are frequent, and the heliospheric current sheet is particularly wavy and turbulent. Could it be that the patch of sky we call Leo in November and December of 2025 was precisely aligned with a high-stress heliospheric sector? If so, then any comet, regardless of origin, passing through that region at that time would be subjected to an extreme space weather event. K1, being a fragile, pristine Oort cloud object, succumbed quickly, turning gold and fragmenting in a week. 3I, with its tougher, thermally processed interior, is taking longer to show the full effects, but the same environmental scalpel is stripping it bare. This would explain the temporal coincidence without requiring any mystical connection between the two comets. They simply walked into the same cosmic storm. Proving this is another matter. It requires correlating the precise 3D trajectory of each comet with real-time in-situ maps of the heliospheric current sheet and solar wind parameters, data that comes from a fleet of spacecraft like ACE, SOHO, and Parker Solar Probe, but which must be extrapolated through vast volumes of space. It's a daunting modelling challenge, yet if 3I does fragment while still in Leo, the impetus to solve that challenge will become immense. This environmental hypothesis transforms December 19th from a simple close approach into a perfectly designed laboratory experiment. On that date, 3I Atlas will pass just 0.28 astronomical units from Earth, a mere 42 million kilometers. In cosmic terms, it's a hair's breadth. This proximity is a gift of immense value. It means the object will be extraordinarily bright in our skies, accessible to large professional telescopes and dedicated amateurs alike. We will not be squinting at a faint, fuzzy speck. We will be studying a resolved, brilliant worldlet. But the true perfection of December 19th lies in its celestial timing. It is a new moon. The moon will be a silent, dark disk between us and the sun, completely absent from the night sky. Lunar glare, the eternal enemy of the deep sky observer, is zero. The background sky will be as black as it can be from Earth's surface, maximizing the contrast between the golden comet and the void. For an object whose signal might be fading, whose details might be subtle, this darkness is not a convenience. It is the difference between seeing and guessing. Furthermore, the geometry is sublime. For the great observatories of the Northern Hemisphere, in Hawaii, the Canary Islands, Arizona, and Chile, 3I will be high in the sky, near the zenith for some. Observing an object high up means looking through the least possible amount of Earth's distorting atmosphere. Southern Hemisphere sites will have a good view as well. This global coverage is not by accident. From the moment 3I's hyperbolic orbit was confirmed, an international campaign was mobilized. Telescope time on the world's most powerful instruments, the VLT, Keck, Gemini, Hubble, and countless others, was urgently repurposed or specially allocated. A coordinated observation plan was drawn up, ensuring that as Earth turns, the comet never slips from the watchful gaze of a world-class instrument. We have never before had such advance warning, such perfect observing conditions, and such global coordination for an interstellar object. This is our best shot, our only shot, to decode its message. So what precisely will they be looking for? The diagnosis of stability or doom will come from 4 intertwined lines of evidence, each a vital sign for the comet. First, and most immediate, is the light curve, the precise tracking of its brightness over time. If 3I begins to fragment, the total surface area reflecting sunlight will initially increase as new faces are exposed. This often causes a sudden brief surge in brightness, a last brilliant flash before the dimming begins. A steady, smoothly varying light curve suggests a single, coherent body rotating peacefully. A jagged, spiking, or erratic curve is the heartbeat of an object in chaos. Second is spectroscopy. This is the forensic tool. They will be watching for specific spectral lines to appear or vanish. A surge in sodium emission would be a telltale sign of fresh, previously buried material being exposed, a classic fingerprint of fragmentation. A continued absence of carbon lines would confirm the volatile depletion is total. New silicate features would indicate we are seeing deeper, dustier layers. The spectrum is a live chemical readout of the comet's interior, broadcast across 42 million kilometers. Third is morphology, the shape. High-resolution adaptive optics on giant ground-based telescopes and the keen eye of Hubble will look for any distortion in the coma. A single, point-like nucleus embedded in a smooth, symmetric haze speaks of health. Multiple condensations, elongations, or jet structures pointing in conflicting directions are the visual signatures of a body breaking up. Even if the fragments are too close to resolve as separate dots, their combined light will create an asymmetrical lumpy glow. Fourth is motion. Using ultra-precise astrometry, astronomers will measure the comet's position against the background stars to an accuracy smaller than an arcsecond. If the nucleus has split, the pieces, though initially moving together, will have infinitesimally different velocities. Over hours and days, those differences will cause them to drift apart. This diverging motion, detectable as a subtle smearing or as multiple tracked positions, is the final, incontrovertible proof of fragmentation. The collective data stream on December 19th will be overwhelming. It will flow in from telescopes on every continent, across the electromagnetic spectrum. The global astronomical community will be holding its breath, watching these 4 diagnostic channels, waiting for the verdict to emerge from the noise. Will we see the deadly brightness surge? Will the spectrum scream sodium? Will the images show a double heart? Will the tracking reveal a divorce in motion? Or will the golden visitor simply glide past, steady, symmetric and silent, a relic surviving its passage? The machines are pointed, the algorithms are primed, the world is watching. And in the heart of Leo, a visitor from another star holds its fate and a piece of our understanding of the cosmos in its fragile, gilded hands. The unspoken fear that hums beneath the scientific urgency is not that 3I Atlas will break apart. Comets fragment all the time. It is a routine cosmic demolition. The fear is that we'll watch it happen with all our technological might and still not understand why. That an object carrying irreplaceable information about the formation of another star system will disintegrate before we can fully decode its message. The gold colour, the Leo coincidence, the K1 parallel, these are not just quirks, they are clues to a larger process, a chapter in comet physics we haven't yet written. If 3I fragments, we lose the primary evidence. The pieces will fade, their trajectories will become uncertain, and the unique chemistry of a baked interstellar core will be scattered and lost. We will be left with the clues, but not the culprit. To appreciate the fragility at play, we must move past the poetry of dirty snowball and understand the brutal mechanics of a comet's death. Comets are not solid. They are rubble piles, aggregations of dust, rock, and frozen gases held together by the feeblest of forces, their own minuscule gravity and, crucially, the structural glue of ices. Imagine a conglomerate of gravel, sand, and boulders, with the gaps filled not with mortar, but with frozen water, carbon dioxide, and carbon monoxide. This ice is not just payload, it is infrastructure. It binds the non-volatile components, providing cohesion. As the comet approaches the Sun, this ice sublimates, turns directly from solid to gas. Normally, this gas escapes through natural pores and fissures, jetting into space and creating the beautiful, structured tails we admire. This outgassing is a pressure release valve. But if the heating is too rapid, or if the internal structure is too sealed, the pressure can build. The escaping gas doesn't just leave, it excavates. It can blow open new cracks, tunnel out caverns, and undermine the integrity of the matrix. When the pressure exceeds the tensile strength of the dusty lattice, the object doesn't explode, it simply comes unglued. The ice that was holding everything together is now gone, and what remains is a pile of loose aggregate with no reason to stay together. For a small body a few hundred meters across, self-gravity is almost a joke. The escape velocity might be centimeters per second. A dust grain given the gentlest nudge will drift away forever. The thin crust hypothesis for 3I Atlas is a specific and terrifyingly plausible version of this death spiral. The gold colour tells us the volatile ices near the surface are gone. The green coma has vanished, meaning carbon-bearing gases have stopped. If the volatiles are depleted, the glue is gone. What we are looking at, then, is potentially a hollowed-out shell, a fragile, brittle crust of dust and rock, perhaps centimeters or meters thick, covering a network of empty voids left behind by violently escaped gas. This crust has no internal support. It is like the hardened foam on top of a drying cup of hot chocolate, riddled with bubbles beneath. Now subject this brittle shell to the stresses of space. The uneven heating of rotation, the hot side expands while the cold side contracts. The centrifugal force of spin, the gentle but persistent pressure of sunlight itself, radiation pressure. These forces, negligible to a solid asteroid, are more than enough to crack a desiccated crust. The fragmentation, when it comes, would be a quiet crumbling, a collapse inward, and a gentle drifting apart. The comet wouldn't be torn apart, it would simply cease to be a coherent object. This is what many privately fear has already happened to 3I. The rapid colour shift wasn't an evolution, it was a diagnosis. The patient was already terminal when the symptom appeared. The gold is the colour of the relic, the tombstone. The only question is how long the gravitational and frictional forces within the rubble pile can maintain the illusion of unity before the final collapse. December 19th might be the day we witness that collapse in real time. Scientists are notoriously reluctant to make public predictions about fragmentation. The history of comet science is littered with bold forecasts that proved spectacularly wrong. Comets that looked doomed have held together for years. Comets that appeared robust have vaporized overnight. The physics is hideously complex, chaotic, and dependent on unknown internal parameters. You can model thermal stress, calculate tidal forces, and estimate tensile strength until your supercomputer smokes, but it all hinges on a giant unknown, the internal structure. We cannot see inside. Our best guesses come from density estimates derived from non-gravitational forces, how much the comet's path deviates from pure gravity due to rocket-like effects from asymmetric outgassing. But if outgassing has stopped, as the gold colour suggests, that window closes. We are left guessing in the dark. This is why in official circles you hear cautious, measured language. But in private emails, on secure video calls between collaborators, the concern is palpable. The K1 precedent is the ghost at the feast. It turned gold and fragmented in 7 days. 3I turned gold on December 3rd. 7 days later was December 10th. As of now, it is still intact. Does that mean it's safer? Or does it mean the clock ticks differently for an interstellar baked core? Is the collapse slower, more methodical? Or are we just witnessing the same process on a delayed fuse? No one knows. And that unknown, the possibility that we are missing a key piece of the puzzle, is what fuels the silent anxiety. This isn't about being right or wrong. It's about the agony of potentially losing a unique dataset to a process we can observe, but not comprehend. This fear, however, is intertwined with a thrilling possibility. Because to understand why it might break, we must first understand what it's made of. And when we point our spectrographs at 3I Atlas, the chemistry we find isn't just strange, it's alien in the most literal sense, pointing to a formation environment utterly unlike our own solar system's quiet nursery. The chemical anomaly that severed 3I Atlas from any simple explanation emerged from the cold, precise data of spectroscopy. In late November, as the green glow was fading, instruments at the Very Large Telescope detected an unexpected strong emission line at 352.4 nanometers. This wavelength is a fingerprint, and it belongs to atomic nickel vaporized by solar heat and glowing in the ultraviolet. Finding metals in a comet's spectrum is unusual but not unprecedented. When solar heating becomes intense, trace metals locked in dust grains can be liberated and glow. What happened next, however, sent spectroscopists back to their raw data in disbelief. Right beside the nickel line in the spectrum, there should be another, a companion signature, the line of atomic iron. In nature, nickel and iron are inseparable siblings. They are forged together in the cores of massive stars during the final stages of nucleosynthesis and scattered together in supernova explosions. They condense together in the dusty disks around young stars. They are found together in every meteorite, in the core of our planet, in the alloy of every piece of steel. Their cosmic abundance ratio is a known quantity. When you find one, you find the other, always, except here. The spectrum of 3I Atlas showed a clear, strong nickel line. The iron line was absent, not diminished, not blended, absent. This is not just unusual, it is a violation of a fundamental galactic chemical rule. It's chemistry behaving in a way that has no ready explanation in the standard playbook of solar system formation. The immediate reaction was to check for error, calibration faults, instrumental artifacts, data reduction glitches. Every check came back clean. Other telescopes confirmed the result. Nickel was present, shouting its signature. Iron was silent. The hypothesis that has gained the most traction among chemists and planetary scientists is as fascinating as it is bizarre. Metal carbonyls. These are volatile compounds where metal atoms, like nickel or iron, bond with carbon monoxide molecules. The most famous and notorious is nickel tetracarbonyl NiCO4. It is a villain in industrial chemistry, colourless, extremely toxic, and volatile enough to boil at a mere 43 degrees, 109 degrees Earth. Its significance here is profound. At the temperatures a comet experiences in the inner solar system, nickel carbonyl can sublimate directly from solid to gas, just like water ice does, but at much, much lower temperatures. Iron pentacarbonyl, FeCO5, also exists but is far less stable. It decomposes more readily under ultraviolet radiation, breaking apart before it can produce a strong persistent emission line in a spectrum. So, here is the scenario that now sits on the table. In the outer reaches of 3I's home star system, in a region rich in carbon monoxide gas, free metallic nickel atoms, somehow liberated from silicate minerals, interacted with the CO under cold, low-pressure conditions. They formed nickel carbonyl. This volatile compound then froze into the growing matrix of the proto-comet. It survived the object's eventual ejection and its millennia-long journey through interstellar space. Now, as the sun heats 3I, the nickel carbonyl sublimates, releasing nickel atoms into the coma where they are excited by sunlight and emit their characteristic glow. The iron, if it was ever present in a form that could make carbonyl, either didn't form the compound or its carbonyl decomposed completely during the journey, or in the current solar radiation field, leaving no gaseous iron to detect. This elegantly explains the observation, but it opens a chasm of new questions about the object's origin. Why would 3I have conditions ripe for forming nickel carbonyl but not preserve iron carbonyl? What kind of environment favours one metal over the other in this way? The answer points squarely away from a quiet, pristine nursery. Free metallic nickel doesn't just float around in cold molecular clouds. It has to be liberated from within silicate rock grains through intense processing, high temperatures, shock waves, or intense radiation. The presence of nickel carbonyl suggests 3I formed in a region that was both carbon monoxide rich and had been thermally or shock processed enough to produce free nickel. This is not the calm, cold outer disk where our solar system's comets formed. This is a region that has been cooked. It could be closer to the parent star, bathed in intense ultraviolet light. It could be a region scoured by shockwaves from a nearby supernova or from violent stellar winds. It could be material that was repeatedly cycled through the inner disk, heated and cooled, chemically altered. This is the heart of the baked core hypothesis. 3I Atlas is not a pristine interstellar iceberg. It is a refugee from a violent kitchen. It is an old, thermally processed comet that had already survived multiple close passes to its home star, losing its light volatiles and having its chemistry altered, before being gravitationally punted into the void by a migrating giant planet. By the time it began its interstellar journey, it was already a depleted, rocky, dusty core, possibly with pockets of strange refractory volatiles like nickel carbonyl trapped within. This stands in stark contrast to our other interstellar visitor, Comet Borisov. Borisov was pristine, volatile-rich, and chemically indistinguishable from a fresh solar system comet. It was a piece of a calm, familiar nursery. 3I is a piece of a forge. This dichotomy is revolutionary. It tells us that other planetary systems are not just copies of our own. They are dynamic, chaotic, and violent. Some, like Borisov's home, may be serene. Others, like 3i's birthplace, are evidently brutal, ejecting material that has been roasted and reformed. The galaxy is sending us a diversity of messengers, and 3i is the first to speak of fire and metal. This baked origin story directly informs its current behaviour and fate. A thermally processed core is denser, less porous, and more cohesive than a fluffy Oort cloud object. It has already withstood great heat. This could mean it is more resilient, explaining why it might have survived past K1's 7-day fragmentation deadline. But it also means its volatiles were already scarce. The brief green phase we saw might have been the last gasp of a thin frosting of surface ices accumulated during its interstellar journey, or the final venting of deeply buried pockets. Once that was gone, it reverted to its true, barren nature, a gilded, dusty relic. This leads to the final chilling layer of its composition, the interstellar frost itself, and why its disappearance is the key to everything we are witnessing now. Interstellar space is not a perfect void. It is a diffuse medium, a thin soup of gas, dust, and radiation. For the millions of years 3i Atlas travelled between stars, it was ploughing through this material at tens of kilometres per second. Microscopic dust grains, silicates, carbonaceous particles, ices of water and other molecules struck its surface and stuck. Water molecules, liberated from other icy bodies by cosmic rays or generated by chemistry in dark clouds, condensed onto its cold nucleus. Complex organic molecules, the building blocks of life known as tholins, formed in situ or accreted, painting the surface a deep reddish brown. This accumulated layer, this interstellar frost, is a travelogue, recording the chemical history of the galactic neighbourhoods the comet passed through. It is why Oumuamua appeared so red. It is why Borisov had organic signatures that seemed slightly off from our own comets. And it is why, when we first detected 3i Atlas in August 2025, far beyond Mars, it too glowed with a dull reddish hue. It was wearing its journey on its sleeve. Then, as it crossed the waterline, the distance from the sun where solar heating becomes sufficient to consistently sublimate water ice, a predictable sequence began. First, the outermost, most volatile frosts boiled away. The colour shifted from red to a more neutral white, as water vapour and carbon dioxide created a diffuse scattering coma. Then, as heating penetrated deeper, carbon-bearing molecules were activated, and the characteristic green glow emerged. For a few weeks, 3i looked like a normal, active comet. But this was an illusion. We were not witnessing the awakening of a pristine interior. We were watching the systematic removal of a temporary coat. The sun was acting as a cosmic blowtorch, stripping away the accumulated frost of interstellar space. The green phase represented the sublimation of the most volatile components of that frost. And then, abruptly, the frost was gone. We had reached the true surface, the original thermally processed core that had left its home star system millennia ago. That core, baked and depleted, had no vast reserves of native water ice or carbon monoxide to sustain outgassing. The gas production ceased. The small dust entrained in that final gasps of frost sublimation was swept away by radiation pressure. What remained was the heavy, reflective, metallic and silicate dust grains that had always constituted the comet's true body. The gold colour is the colour of the bare nucleus, finally revealed after its long journey. This is not a chemical transformation, it is a physical unveiling. The comet has molted, shedding its interstellar skin to show us what it has been all along, a relic. This narrative of layers, interstellar frost over a baked core, explains the rapidity of the transition. The frost layer, while cosmically significant, was likely only meters or even centimeters thick. Once solar heating worked through it, the shift from active to inert would be swift, because the underlying material is inert. The 5-day change wasn't an internal collapse, it was the final brushstroke of solar wind wiping clean a window. But this unveiling has a terrifying structural consequence. That frost layer, however thin, provided cohesion. Water ice, even in trace amounts, acts as a cement. In the extreme cold of interstellar space, it welded dust grains together, filling pores, adding structural integrity. Now it is gone. The nucleus we are now seeing is, according to this model, a loose aggregate of dust and rock whose only binding force is its own negligible gravity, and any remaining electrostatic forces. For an object a few hundred meters across, this is a precarious state. The escape velocity is so low that a gentle push from photon pressure, or the slight torque from asymmetric heating, could begin lofting grains away permanently. The object isn't being torn apart, it is slowly, grain by grain, dissolving. This is the most likely fragmentation mechanism for 3I. Not a catastrophic split, but a gradual quiet disintegration, a shedding of its constituent parts until nothing coherent remains. December the 19th, under the exquisite resolution of our telescopes, may show us the beginning of this dissolution, not as dramatic fragments, but as a halo of drifting debris, a permanent expanding fog where a nucleus once was. This understanding forces us to reconcile the two competing camps that have formed within the astronomy community, each interpreting the same data through different lenses. The fragmentation camp, anchored by the K1 precedent, sees a clock ticking. The rapid colour shift is a symptom of catastrophic volatile loss, a sign of internal venting that precedes structural failure. The gold is the calm before the storm. They point to the object's faintness relative to size estimates, as evidence that mass loss is already underway, perhaps through unseen microfragmentation. Their prediction is clear. December 19th will reveal a breakup in progress. The survivability camp, however, argues from composition and history. 3I is not K1. It is a thermally processed baked object. It has already survived the fire of its home star. The loss of volatiles means there is no internal pressure left to drive an explosive fragmentation. It is now an inert rocky body, more akin to an asteroid than a comet. Such objects don't spontaneously fragment without extreme external stress like a tidal disruption or collision, neither of which is happening. The gold colour, they argue, is a stable endpoint, not a prelude. The comet will pass by, a silent gilded monument, and fade as it recedes. Both camps have evidence, both are plausible, and both are haunted by the third unspoken option, that we are still fundamentally misunderstanding what we are looking at, and 3I will do something entirely novel, leaving both camps wrong and the field in a state of thrilling confusion. This intellectual tension is the engine of science. But there is a fourth layer to the debate, one that has been simmering since the Leo coincidence was noted: the role of the environment. What if the trigger for whatever happens next is not intrinsic to 3I alone, but is found in the specific region of space it is now traversing? The non-random hypothesis moves the conversation from what the comet is to where the comet is. It posits that the patch of space corresponding to the constellation Leo during this specific temporal window is a region of enhanced heliophysical stress. This isn't mysticism, it's an exploration of whether local space weather can act as a catalyst for comet evolution. The sun's magnetic influence structures the solar system into sectors of varying magnetic polarity, particle density, and wind pressure. The heliospheric current sheet, the wavy boundary between these sectors, is a zone of complexity. During solar maximum, the phase we are in now, this sheet is highly distorted, creating pockets of intensified interaction. Charged particles are accelerated, magnetic fields are tangled, and the solar wind is less a steady breeze and more a series of gusting fronts. If a comet's trajectory carries it through a particularly disturbed sector, the environmental effects could be significant. Enhanced solar wind pressure could mechanically compress the coma, accelerating the stripping of gas and fine dust. Energetic particles could sputter surface material, sandblasting atoms away. Complex magnetic fields could interact with ionized gas in the coma, inducing currents and localized heating. The hypothesis is that K1 Atlas, fragile and pristine, entered such a sector and was rapidly stripped and destabilized, leading to its gold transition and fragmentation. 3I Atlas, entering the same sector weeks later, is undergoing the same environmental assault. Its tougher, baked constitution means the process is slower, the colour change came first, but the destabilization may still be underway. The fragmentation, if it comes, would then be the result of this external sandblasting and weakening an already fragile structure to the point of collapse. This idea is compelling because it offers a physical mechanism for the correlation without requiring a mystical link between the two comets. They didn't influence each other, they both walked into the same cosmic weather system. The resistance to this idea in some quarters is not scientific but almost sociological. It sounds, to the cautious ear, perilously close to astrology, the debunked idea that positions of stars influence events. Scientists are rightfully terrified of giving any quarter to pseudoscience, so they retreat to the safe ground of intrinsic properties, composition, density, temperature. These are clean, controllable variables. Environmental triggers are messy, harder to model, and require correlating disparate datasets from heliophysics and planetary science. But ignoring a potential correlation because it's uncomfortable is itself unscientific. December 19th serves as a crucial test. If 3I fragments, while still positioned against Leo, the environmental hypothesis gains significant weight. If it waits until it has moved into the next constellation, Virgo, or never fragments at all, the focus will swing back to intrinsic causes. The data collected will be scrutinized not just for what it says about the comet, but for what it might say about the invisible structure of the space it is flying through. This moment represents a potential convergence of fields where comet science must engage seriously with the dynamic, structured nature of the heliosphere. It is a reminder that objects in space do not move through a passive, empty stage, but through a complex, evolving medium that can itself be an actor in their drama. This entire investigation is being conducted at a pace and scale never before possible, thanks to a silent partner, artificial intelligence. The discovery of 3I Atlas itself was an AI-assisted event. The Asteroid Terrestrial Impact Last Alert System, ATLAS, survey uses machine learning algorithms to sift through millions of nightly detections, flagging objects with unusual motions. It was an algorithm that first calculated 3I's hyperbolic orbit and raised the priority alert. But AI's role is expanding far beyond discovery. It is now used to monitor the comet's light curve in real time, identifying subtle anomalies human eyes might miss. It correlates spectroscopic data against vast libraries, instantly flagging the absence of the iron line. It analyzes high-resolution images for morphological changes suggestive of prefragmentation. These systems operate in high-dimensional parameter space, finding correlations between color, brightness, solar wind data, and sky position that a human researcher, focused on one specialty, would likely never see. An AI has no intuition, but it also has no bias. It doesn't dismiss a faint, unusual signal as noise because comets don't do that. It simply flags it as an outlier. 3I Atlas is a symphony of outliers: interstellar, rapid color change, strange chemistry, positional coincidence. To an AI trained on normal solar system behavior, it screams for attention. This partnership, machine intelligence for pattern recognition at scale, human intelligence for hypothesis and understanding, is defining modern astronomy. It ensures we are not just watching 3I but seeing it in the fullest possible context. And as we watch, we must also look ahead. The story of this visitor does not end at Earth. Whether it survives December 19th or shatters, its path leads it deeper into the gravitational grasp of the solar system's true heavyweight, Jupiter. Jupiter is the gravitational titan of our solar system, a sculptor of orbits and a breaker of worlds. Its influence extends far beyond its visible disk, a sphere of dominance that will be 3I Atlas's next great challenge. In late 2026, assuming its current trajectory holds, the interstellar visitor will pass within roughly 2 astronomical units of the gas giant. While this is not a close flyby by cometary standards, nothing like the fateful pass that tore Comet Shoemaker-Levy 9 apart, it is well within the zone where Jupiter's tidal forces become a serious consideration for a fragile body. This encounter will be a test of a different kind. The December 19th passage tests thermal and internal structural integrity. The Jupiter encounter tests pure gravitational resilience. Tidal forces are not about the strength of gravity at the object's center, but the difference in gravity across its width. Jupiter pulls harder on the side of the comet facing it than on the far side. This differential pull creates a stretching stress. For a strong, monolithic body like an asteroid, this stress is negligible. For a rubble pile held together by the faintest whisper of gravity and the last remnants of icy cement, it can be the final straw. If 3I survives Earth flyby, but is in a weakened, unglued state, a loose aggregate of dust after the loss of its frost and volatiles, then Jupiter's gentle tidal gradient may be enough to tease it apart. The fragments wouldn't be blasted away, they would simply drift apart on slightly different trajectories. a silent and slow-motion disintegration over weeks or months. This would be a second chance to observe fragmentation mechanics, but in a purely gravitational regime, offering contrasting data to any thermally driven breakup we might see in December. Furthermore, Jupiter's environment is not just gravitational, it is radiological. The planet's immense magnetosphere is the largest structure in the solar system, a trap for an accelerator of charged particles that creates radiation belts millions of times more intense than Earth's. Passing through the fringes of this magnetosphere, 3i would be bathed in an extreme flux of energetic electrons and ions. This radiation could have several effects. It could cause intense surface charging, leading to electrostatic levitation and loss of fine dust grains. It could induce sputtering, knocking atoms directly off the surface through particle impacts. It could even trigger complex radiation chemistry in any remaining surface ices, creating new exotic compounds. We have never observed an interstellar object interacting with a giant planet's magnetosphere. The data, if 3i remains observable, could be unique. It would tell us about the object's electrical properties, its surface material strength, and its response to an environment utterly different from the quiet of interstellar space or the gentle heating of solar photons. The Jupiter encounter, over a year away, is already being planned for by forward-looking research teams. Telescope time on facilities that can track faint objects in 2026 is being tentatively reserved. The encounter may lack the dramatic proximity of December 19th, but its scientific value is immense. It represents a long-term experiment in interstellar object durability. Whether 3i reaches Jupiter as a single entity or a cloud of debris will fundamentally shape the questions we can ask. A coherent survivor would allow us to study how an alien baked core withstands tidal stress, informing models of exocomet interior structure. A dispersing cloud would allow us to study the dispersal dynamics of interstellar material within our system, tracing how another star's debris is incorporated into our local environment. Both are valuable outcomes. This forward-looking perspective underscores the most important lesson 3i Atlas is teaching us. Even before its fate is decided, interstellar objects are not just rare curiosities. They are a diverse population, and we are only beginning to sample them. The trio of interstellar visitors we have now, Oumuamua, Borisov, and 3i Atlas, presents a portrait of extreme diversity, not uniformity. Oumuamua was an inert, tumbling rock with no coma and non-gravitational acceleration, so anomalous it sparked legitimate, if fringe, debates about artificial origins. Borisov was a carbon copy of a solar system comet, pristine and volatile rich. 3i Atlas is something else entirely. Thermally processed, volatile poor, chemically anomalous. 3 visitors, 3 radically different profiles. This is not what simple models predicted. If planetary systems form by similar rules, we expected interstellar objects to be broadly similar to our own. Instead, we're getting a catalogue of difference. This tells us that the galaxy is a factory producing comets and asteroids in a vast array of environments and histories. Some systems are calm and orderly, ejecting pristine material from their outer disks, Borisov. Others are violent and chaotic, roasting their inner material and ejecting processed cores, 3i. Some produce strange elongated objects through processes we don't yet understand, Oumuamua. The interstellar object population is a statistical sampling of galactic planetary system evolution. Every one we catch is a snapshot of conditions around another star. 3i's baked core and nickel chemistry are not anomalies. They are data points in a distribution we are just beginning to map. This realization humbles our solar system-centric models. We built our theory of comet formation from one example, our own. Now we have evidence that our example might be just one flavor in a cosmic ice cream parlor of possibilities. This has profound implications for understanding how common or rare our kind of system is, and for interpreting the chemical fingerprints we will one day see in the atmospheres of exoplanets. The study of these visitors is being revolutionized by 2 quiet revolutions: dust physics and artificial intelligence. For decades, the gold color was a mystery because our models of light scattering by cometary dust were too simplistic. We assumed small, fluffy grains. Recent laboratory work has shown that gold reflection emerges naturally from populations of larger, compact, reflective grains, exactly the kind left behind when small dust is swept away and gas production stops. The mystery of the colour is being solved not by astronomy, but by precise laboratory astrophysics. Similarly, the flood of data from all sky surveys is now so vast that only AI can mine it effectively. AI found 3i. AI monitors its health. In the future, AI will correlate its behaviour with solar wind data to test the environmental hypothesis in ways humans could not manually perform. These tools allow us to move from simply observing to deeply interrogating these visitors. So we arrive at the precipice of December 19th. Let's play out both futures. In one, the golden point of light holds steady. Its brightness is unwavering. The spectra are stable. The images show a single, symmetric nucleus. 3i Atlas survives its close approach, a silent, gilded envoy passing by. It will fade as it journeys toward Jupiter, and we will have learned that thermally processed interstellar cores can be robust, that gold is sometimes an endpoint, not a prelude, and that the K1 coincidence was, however improbably, just that. But we'll still not know why the nickel is without iron. We will still lack a complete model for its formation. The Leo coincidence will remain an unresolved statistical curiosity. In the other future, the data stream on December 19th turns chaotic. A brightness surge flickers and fades. Spectroscopy screams with sodium. Images reveal a bilobed shape, then multiple points of light. Astrometry confirms divergence. 3i Atlas fragments before the world's assembled telescopes. We will have witnessed the death of an interstellar comet. We will have a wealth of data on the process, but we will still debate the cause. Was it the final failure of a desiccated crust? Was it the delayed action of the same environmental stress that killed K1? Was it a chain reaction begun weeks ago that we only now see culminate? The primary evidence, the intact nucleus, will be gone, scattering the answers with it. Both outcomes leave us with questions. This is the true legacy of 3i Atlas. It is not here to provide neat answers. It is here to expose the gaps in our understanding, to show us which of our models are too narrow, which questions we have been too timid to ask. The gold colour, the Leo sector, the nickel anomaly, they are interconnected threads pointing to a richer, more complex reality of comet life and death, where intrinsic composition and external environment interact in ways we're only beginning to appreciate. It has taught us that the galaxy is stranger and more diverse than we imagined, sending us messengers of fire and ice, of pristine snow and baked stone. On December 19th, we will learn something. We will add a critical data point. But the larger story, the story of how the galaxy builds and scatters its smallest worlds, will continue to unfold long after 3i has faded from our view. Our job is not to be right, but to pay attention, to stay curious, and to let the cosmos, in its infinite creativity, guide us to better, harder, more profound questions. The Golden Visitor, whether it survives or shatters, has already succeeded in that. It has made us look up and wonder, with a little more humility and a lot more excitement, at the strange and wonderful universe we inhabit.